Hi everyone, this is Daniel doing the week 11 worksheet walkthrough for question number 4. This question will be dealing with multiple distributions in a problem. So yeah, let's get started. So question says that we're a professor doing research in ML, and on average we receive 12 emails per day from students. But this number varies. Sorry about that, just charged my computer. Okay, so what we can see from this distribution then is that we're trying to measure some number of some occurrence, and this happens regularly, and this also happens independently of each other. So it should sound pretty familiar to you, but this distribution sounds like it should be a Poisson distribution. And we're given that the expected number of emails per day is 12. So the parameter should probably be 12. Great. And that's it for part A. So moving on to part B. The question is, okay, then what is the probability that you receive 7 emails tomorrow? And then what is the probability that you receive at least 7? So first thing to note is that the probability that you receive X amount of emails tomorrow is the exact same as, X amount of emails 5 days from now, a billion years from now, 3 days from now, under the context of this problem. So this is due to the memoryless property of distributions. So let's just focus on the 7 emails. Well, what is the probability that, let's call our random variable x equals 7. And I guess I should define this here as well to make it explicit. Well, we know that the formula for the probability of a Poisson distribution is given by our parameter to the ith power over I factorial times e to the negative lambda. So plugging in 7, we have e to the negative 12 over 7 factorial times 12 to the 7th. And this is the answer, and it comes out to be 0.0437. Great. Now, what about the probability that x is at least 7, so greater than or equal to 7? Right? So we're asking the emails we receive tomorrow is at least 7 or exceeds 7. So one thing to note here is that unlike perhaps a geometric distribution, there is no closed form formula for kind of determining the tail end of a probability distribution. You might remember that for a geometric distribution, you have something like probability that some geometric distribution is greater than some number. Geometric random variable is greater than some number. Can be given by p minus 1 minus p all to the let's say k minus 1, right? Because if our success happens on the kth trial, that means that the first k minus 1 trials all fail. So that doesn't exist for the Poisson distribution. So instead we have 2 options. We can, one, just count up every single probability going from 7 all the way up to infinity, because you can receive 7 emails, 8 emails, 9 emails, all the way up to the 10, all the way to infinity emails, and that will look something like this. So the sum from, let's call this k equals 7 all the way to infinity of e to the negative 12 times the 12 to the kth power over k factorial. Problem with this, obviously, is there's no clean way you can think of how to solve it. So instead, we can, you take advantage of this word at least and realize that, the complement of this is far easier to find, which is probability x is strictly less than 7. And by the total probability rule, we know that probability that x is greater than 7 is equal to 1 minus the probability of x being less than 7. Great. So then what's the probability of x being less than 7? Well, unfortunately, there is again no clean formula. We just have to sum up all the probabilities from 0 to 100, 0 to 7, and this will look something like this. Probability that x equals 0 plus probability that x equals 1, x equal to 7. And for each of these, we just plug in the same Poisson formula, which is given by, I'll just do this term to show you, e to the negative 12 times 0 to the, sorry, that's wrong, 12 to the 0th power over 0 factorial, negative 12. And same thing for these and these. And in the end, the answer that you should come out with is not good, because it's not important. But that's how you would find this answer. Both these formulas will take you there. Great. So now let's move over to part C, where we're asked, okay, let's look at the month of April, in which lots of students are emailing you to secure a summer position. What's the probability that the first day in April you receive, the first day in April that you receive exactly 15 emails is April 8th? Okay, well, this looks a little bit challenging. So a good way to start might be, let's just convert this from writing into math terms, right? So what we're asked to find is the probability that receive 15 emails on day X and day perhaps and X equals 8, right? We're looking for the 8th day. Okay, well, this looks pretty horrible and very annoying. But one interesting thing is that we now have this sort of X variable here, along with this, general probability statement. Well, so that should kind of make us think, okay, maybe multiple distributions are involved in this thing. Going with that intuition then, let's first try to see, okay, what's just generally the probability of finding exactly 15 emails? And we know that our distribution is a Poisson distribution, so the probability that we receive 15 emails on some day, whether it's April 8th or whatever, it should be the same, equals e to the 12 times 12 to the 15 all over 15 factorial. And to make our lives easier, let's just set this equal to something let's call p. So we don't have to keep on rewriting this sort of expression. It's kind of annoying. Cool. Now moving on to the second part. Well, now that we have this probability for receiving 15 emails, we want to know what's the probability that we receive 15 emails. The first time we receive 15 emails is on April 8th. So if you think about this for a little bit, you might start to see that, well, the only way the first time we receive 15 emails is on April 8th is if April 1st, 2nd, 3rd, 4th, all the way to 7th, we don't receive 15 emails. And after April 8th, this really doesn't matter anymore. So this kind of distribution of failing to succeed X amount of times and then succeeding the last time should remind you a bit of the geometric distribution. And that's exactly what this is. So what we have then is that the probability that, let's call this first day on 8th should be, well, we have to have failed to get 15 emails on the first 7 days. So we should have 1 minus p to the 7th power. And on the 8th day, we should have succeeded in getting 15 emails, so times p. And that is indeed the answer. And once we plug in this expression right here, we get the answer of 0.0427. Write that a little neater for you guys. That is it for part C. Great. So now let's move over to part D, where we're asked, I calculate the probability that April 8th is the first day we receive at least 15 emails. Well, so building on this from part C, we see that we kind of isolated this probability P as its own variable, and we didn't really even include it that much in solving the equation. It's just a constant you have to plug in. So in the same way, to find the probability that you receive at least 15 emails exactly on April 8th, we can use the overarching, the larger distribution is still the same, being a geometric distribution. The only thing that changes is this p-value we have here. So then in that case, well, what is the probability that, let's say x is at least 15, so that is greater than or equal to 15? Well, remember from part B, we already calculated something similar for 7, right? Probability that x is greater than or equal to 7. We just have to sum them up from all the probabilities up from 7 to infinity, or alternatively, subtract off the first 7 values. So in the same way, we can do this sort of complement trick here to find the value that we're looking for, and that could be given by 1 minus the probability that x is less than 15. So that is, we have to subtract all the cases where we receive less than 15 emails, and we do this by subtracting off the summation from k equals 0 to infinity, sorry, not infinity, 15 of e to the negative 12 times 12 to the k power over k factorial. And this again is just the formula for the Poisson probability function. Probability function. And this number comes out to be 0.22798. Great. So now that we have this number, and the probability of April 8th, let's call it, being this day with at least that's an important thing, that at least, right? 15 emails equals, again, the same distribution, 1 minus p to the 7th times p. So the difference is now this number is p, and not this number right here. Great. And if you're curious, this number comes out to be 0.03726. And that's the answer for part D. Great. So finally, last question. Part E, what is the probability that you receive at least 15 emails on 10 different days in a row? Okay, well, again, we see maybe a good strategy would be just to write it out in math terms, if nothing else, just so we don't have to do it again. At least okay. Doesn't really seem to simplify our expression by that much, but at least now it might be more clear that to see that there's kind of, again, two expressions or two separate things that we might have to calculate. One is this at least 15 emails bit, and then we also have this on 10 different days bit. Okay, well, from our previous part, we actually already know what the probability of receiving at least 15 emails on one day is, right? Probability that, let's say, x is greater than or equal to 15. We already have that, and that's up here. So let's just copy that, paste it right here for ease of calculation, so we just don't have to go back and forth. And now, really, because of the memory list property, right? Again, we know that the probability that we receive at least 15 emails on day 1 day, 5 day, 3 is the same thing, regardless, as long as there's no other funky distribution going on. But in this case, there is another funky distribution, and that is this 10 different days. 10 different days. Okay, so I'm not just any 10 different days, it's 10 different days in April. That's pretty cool. Okay, so now if we were to ignore this funky Poisson distribution constant that we have dealing right here, how would we do this? How would we find the probability of event P happening on 10 different days in April? Well, first, how many days are in April? And I'm ashamed to say I had to look this up, but this happens to be 30. Great. And then what are we asking for? We're asking for 10 different days where event P happened, right? So perhaps to make this even more transparent, let's just come up with one example, right? So what's the possibility that we have this, where we have 10 days where P happens in 30 days? Well, that might look something like P happens on the first day, not on the second day, yes on the third day, not on the fourth, fifth, sixth, seventh, eighth, ninth, here, right? And what you notice is that there should be 30 terms here and 10 P's in this strip. Oh, okay, this looks pretty familiar now. This just looks like a bit string to me. Namely, it looks like the only ways we can the number of ways we can have this 10 successes in 30 days would be the number of ways we can shuffle the string around. And you should maybe recall from counting that we can do this by choosing out of 30 total possible days, 10 days to be the days where event P happens. Okay. Now, bringing this back to our probability that we found up here. Well, now all we need to do is calculate the probability that some event like this happens. So if we have 10 days where P happens, and let's just call this P to make this less annoying. P happens. And 20 days where it doesn't. And all these events happen independently of each other. Then we can just multiply all these probabilities together, right? So then we have finally that the probability that we receive 10 different days in April, 15 emails, is 30, choose 10 ways of this possible ways we can have 10 different days in April to have 15 emails. And for each given combination of events, the probability that this happens is P to the 10th power of 1 minus P to the 20th power, because we have 20 days where we don't receive 15 emails, and 10 days where we do. And just to remind you, we set P equal to this probability over here, which comes from the fact that the probability that we receive at least 15 emails on a given day is this number right here, which we calculated by finding basically just summing up all the ways that this can happen. Great. And now we're basically done. You just plug in the numbers. If you so like, I'll give them here to you as well. But this number comes up to approximately 0.06446. And that's the answer for part E. So thank you guys for listening to this video. I hope you found it helpful, and good luck.